Okay, this video is about the alternating series test. And so when you have a series and they alternate between positive, and negative, that type of series converges if all three of these conditions are met. Each term, so the U1, U2, U3, and U4, each one of those specifically, not the signs in front of them, are positive. Eventually the terms decrease in values, so they keep getting smaller, and the limit of this function, not with the -1 in there, goes to 0. And this test is going to be useful when we check for convergence of an endpoint. So first we're going to use the ratio test to determine what the actual interval is, and then we're going to be using this a lot of times to determine whether or not that endpoints are included in our interval of convergence. Okay, so for the first example, like I was just saying, we use the ratio test. So we have the limit as n goes to infinity. Now this one's kind of crazy. We have n plus 1 x to the n plus 1 over 4 to the n plus 1 times by, in parentheses, n plus 1 squared plus 1. Woo. Now that's going to be multiplied by the reciprocal of that, because remember it's a sub n plus 1 over a sub n. So we have 4 to the n over n squared plus 1 divided by n times x to the n. Okay, so let's look and see what we have to cancel, or what we can cancel here. This 4 to the n plus 1 and 4 to the n cancels to just be a 4 on the bottom. X to the n and this x to the n plus 1 cancel to just be an x on top. So what we have over n squared plus 1 all over 4n, and then we have n squared plus 1 squared plus 1. So on the bottom we would get n to the third, on the top we'd get n to the third, so that goes to x over 4. Now remember from the ratio test, we need this, what our limit equaled, for this to converge to be less than 1. So from -1 to 1, so our interval of convergence is -4 to 4. Now we need to check the endpoints, meaning what we do is we plug in -4 for x in this original summation. Okay, you have 4 to the n, you have -4 to the n. So what we have there is we have n over n squared plus 1. We have same base. Actually, I'm going to erase a little bit. Not the same base, I apologize. Same exponent, so that's going to simplify to -1 to the n. So then what we do is we look at this. The alternating series test works because when I'm plugging in values for n equals 1, 2, 3, 4, this piece is always going to be positive. It alternates by this -1 to the n, and this limit goes to 0. So therefore, this converges by the alternating series test. Now, that means that -4 is included in our interval. Now let's check x equals 4. I apologize. I just sniffled. I have to sneeze, and I'm trying not to sneeze in the microphone. And how this video is set up, I can't pause it. So there we go. Okay, so I apologize. Plugging in 4. And so we have 4 to the n over 4 to the n over n squared plus 1. So this simplifies to, those cancel, n over n squared plus 1, which we can say okay, in my notes, I'm looking at my notes. In my notes, I have limit comparison test. I guess we could also use the direct comparison test. So if I directly compare this to, because this is now approximately, okay, and I should say the direct comparison test, we have to make sure that we show that one function is less than another one. Actually, it's kind of hard to show that this function's less than that one. Maybe that's why I used the limit comparison test. So let's go ahead and do the limit comparison test of n over n squared plus 1 times by the reciprocal of what we have there, which is n over 1. Sorry, I'm looking at my notes. Okay, so that simplifies to n squared on the top, n squared on the bottom, so that equals 1. This diverges by the limit comparison test. So we don't include 4, so that's our answer. Okay, next example. Let's do another one. Okay, so in this one, again, the same thing. You have to do the ratio test to determine what your interval is. Limit as n goes to infinity of the n plus 1 term. Okay, so I have -1 to the n plus 2 times by x to the 2n plus 2, because if I plug in n plus 1 and distribute the 2, all over 2n plus 2. Oh, I forgot my absolute value signs. Then we multiply that by basically the reciprocal of that thing, which is 2n over -1 to the n plus 1. Oh, that's annoying. I apologize, that's annoying. Hopefully that bell wasn't too loud on you guys. X to the 2n. Let's look at what cancels. X to the 2n cancels with x to the 2n. As we go to infinity, these essentially cancel to be a -1, but then we're going to end up taking the absolute value of it. As this goes to infinity, all of this simplifies to be absolute value of x squared. So then our interval is x squared less than 1, meaning -1 less than x less than 1. And then now we have to test the endpoints. X equals -1. So this simplifies to -1 times 3 to the n plus 1 all over 2 to the n. And again, alternating series, each one of the terms, which is 1 over 2 to the n, is positive, and that gets closer and closer to 0. So this converges by the alternating series test. So I include -1. And then now let's test x equals 1. So now we have that. And remember, this is essentially 1 because 1 to any exponent is 1. So what I really have here is -1 to the n plus 1 times by 1 over 2 to the n. And then this also converges by the alternating series test. So I include that point. All of those points are included. And I have 2 more examples, but that kind of gives you a flavor for what we're doing, so I'm going to leave it there. That's all I was going to say. I was going to say something else, but